Thank you all for coming. It's good to see great attendance. And I thought I'd just run through a few things first for those that weren't in my talk yesterday. I recognize lots of faces, so that's great. But what we're basically going to be doing today is setting up the Faucet SDN controller. So it's a controller written mostly in New Zealand, that we have a lot of international collaborations, people working on it as well. It's kind of like the lightweight approach to SDN. So for those who are familiar, OpenFlow is the protocol it uses to program switches. And in 10,000 lines of Python, we pretty much replicate a regular layer 2 and layer 3 switch. We won't be going into the testing or multi-vendor part of Faucet today, but everything we do today on your laptop in a virtual environment works just the same on hardware as well. And we're going to be writing a lot of policy and sort of giving a Faucet a bit of a drive and see what it does. So here's the architecture diagram for Faucet. So we're going to be playing with Faucet Engage today. So Faucet is a OpenFlow controller that you give it a config file. So we're going to be writing a lot of YAML today. Hope everyone's OK with that. It's pretty easy to get your head around. And then Faucet sort of takes a YAML definition of your network. It writes OpenFlow rules for you. You don't ever see them. And it pushes them down to the switch. So the switch at the bottom today that we're going to be using is a thing called vSwitch. Fantastic production quality software switch written in C, which does a bunch of different APIs. And OpenFlow is the one we're going to be using today. And then Engage is our sort of read-only controller. It's for monitoring your network. So you also give it a config file, but that generally doesn't change. And then that's going to poll the switch for statistics. And we're going to have a nice Prometheus database and a Grafana instance that we'll build today. And then we're going to build a router, and we're going to speak BGP to it. And yeah, so we're going to cover 5 sort of tutorial modules today. So the first one is just installing it. It's a pretty easy one. You copy and paste some commands and should all work, hopefully. And then we're going to get into policies, or ACLs as we call them in Faucet, which will start to sort of block some traffic. And then we're going to play with having multiple VLANs on a network to segregate hosts. And we are going to play with some routing, static and BGP routing. And then we're going to do NFV services. And I should probably explain what that means to Faucet. So in Faucet, you can kind of, you can tell the switch you want to steal a packet and send that to somewhere other than like just doing regular MAC learning and switching. And so you might commonly want to do this with like DHCP or something, make sure it goes to the DHCP server and doesn't go anywhere else. In this particular module, we're going to play with some DNS. We're going to sort of hijack a DNS session and send its traffic to a local DNS server and see how that kind of works. And I think what we'll do here is I'll sort of go through the modules one by one, and then we'll try and get everyone sort of to complete the module as well. And if you get stuck, I can come around or answer questions. So hopefully you can all play along and get everything working as well. We've got quite a bit of time, so there's no panic there. And please do ask questions. I want this to be quite interactive. So if you get stuck or something doesn't work, please let me know. So yeah, so let's get started. So could everyone load up this URL, and I'll load it up in a second. And if you want, it's good to do this in an isolated environment, like a VM, like a Ubuntu, something or other. It doesn't really matter. You can run it on your main system if you want. There's some manual cleanup you have to do at the end. I have QCal images and ISOs if anyone's Wi-Fi isn't able to download a sort of VM in time. But has everyone taken note of that? Can I? No? Keep waiting. You can also just go to docs.faucet.nz and click the tutorial section. It'll get you the same place. Maybe I should write it on the whiteboard as well. Cool. They're not very visible. And then we can't see the screen. Okay, it's all right. What we'll do instead, so turn the lights down. So I'll just jump into my VM. And can you see that? I can make the font a bit bigger. So there's just this tutorial section on the side, and we're going to start with installing Faucet for the first time. So let me know when everyone's got that far. I'll just pull off to the side so I can open a terminal. All right, so like our diagram depicted, so Faucet, Gauge, Prometheus, and Grafana we're going to install in this module, and we're going to see them all working together. So yeah, Faucet and Gauge are the controller parts of Faucet. Prometheus is a time series database, and also it is like a powerful query engine for pulling out statistics. So Prometheus is where we store instrumentation for Faucet. It's also where we store all our byte counters, so anything you'd normally get through SNMP is in there. And then Grafana is quite a nice interface to Prometheus, and you can make real-time sort of dashboards. So that's what we're going to be using that for. So hopefully you got some kind of a machine, or you're working towards getting a machine that can run some commands. And I'm just going to go here. So really simple to start off with. We're just going to add the apt repo for Faucet. So it's on Package Cloud, and it's where we put all our releases. I hope everyone's updated their apps. There was a not so great vulnerability that meant someone could inject whatever they could. I updated this one this morning, so we should definitely be good. Okay, so add the GPG key as well for our repo so that we can trust them. And if we do an update, it'll walk all the package lists, and we'll be able to install the packages. I assume everyone can read the text up there. Is it okay? Cool. Okay, now there's this meta package, or like super package for Faucet called Faucet All-in-One. And you wouldn't normally use this in real life because it installs everything for you and puts in some default configs. So there are also individual packages for everything. But for this tutorial, it makes this quite easy, because since we're like a Python project, there unfortunately is a few dependencies that we need to pull in, but luckily they're quite small. And we keep them up to date. So we try and publish deb packages for all the updated dependencies quite regularly to our repository. We publish for all LTSs for Ubuntu, which I think is 3 at the moment, and all supported versions of Ubuntu, which I think is 3 at the moment, Xenial, Artful, and Bionic. And then for Debian, no, which one's not supported anymore?
Trusty, Xenial, Bionic, and Cosmic are currently supported ones. Just wondering if there's some of any.
It's Cosmic, it is released, isn't it? I will show you the CI build script and tell you what actually it is, rather than... No, it's all right, let's have a look. I should know that, since I wrote it. So everything is just built on GitLab at the moment. So Xenial, Artful, and Bionic is what I build on at the moment. So I guess I should make a note to... Yeah, only about every 6 months go through in here and actually update things. And then I support a lot more Debians. Oh, and there's Raspbian as well, so if anyone got a Pi 0, Faucet will run on a Raspberry Pi happily. I don't recommend doing it for large networks, but it does work. All right. Oh, there we go. That gave us enough time to wait for our app to finish running. All right, so the first step we're going to do is configure Prometheus, and we're just going to have a poke at the Faucet. So Faucet ships a Prometheus config when you install that all-in-one package. And we're just going to quickly go through here and explain what it does. So Prometheus is also configured in YAML. It's a common theme that you're going to sense throughout this whole demo / tutorial. So at the top, we set a scrape interval. So the way Prometheus works is it sort of runs as a daemon, and every job or instance it knows about, it goes and does an HTTP GET to a URL and a port number for that service, and it just downloads this big list of every metric with descriptions and values. And so here we're saying scrape everything every 15 seconds, so that means all your data is going to be up to date every 15 seconds. We load a rules file, and in Prometheus what you can do is you can take data and make other data. So it can ingest a bunch of metrics and then do a bunch of computation and produce new metrics. So I'll show you what we do for Faucet in a second. And then what we have here is we have a job called Prometheus, so we're telling Prometheus to monitor itself. We're telling it to talk to Faucet on port 9302 and Gauge on 9303. At the moment, everything's running on my laptop, so everything's going to be localhost. Ah. Is that? Yep. Okay, so we'll just have a look at the rules file. So we've got a bunch of counters in Faucet that we want to transform into gauges or rates. And so this is pretty much all this is doing, is it's taking in sort of counters and putting them into 1 minute metrics and that kind of thing. But and then we do a bunch of stuff like these convert bits to bytes, that kind of thing. And you can come in here and make your own one of these, but those are the default ones. Okay, and then all we need to do is we need to tell Prometheus to load our version, its config, not its version. So etc default Prometheus has this args line, and all you do is you copy and paste the Faucet one into there. And then once you've done that, you can go restart Prometheus, which will trigger it to load that. Now Prometheus comes with a web interface. Sorry, 9090. Okay. If I do that, does it get clipped? Oh, no, that's right. And so in the Prometheus interface, you can look up metrics and it will sort of autocomplete. So if you look at up is kind of just set to 1 always, and you can use up to work out who's talking to you. So the things that are up at the moment is it sees a Prometheus, it sees a thing called node, it sees a Faucet, and it sees a gauge. So that's all we want to get to at this point. It means everything's actually reporting to us. And then we'll go into configure Grafana. So the Grafana package, when you first install it, it doesn't start itself, so you just have to go tell it to start. And then just like with Prometheus loading the web interface, we can load on port 3000, we get Grafana. Oh, I'll make that a bit bigger. So Grafana is just admin. And it's going to tell us we should really change that, but I think we can just hit skip for now. And then Grafana sort of starts with nothing, and then it gives you this kind of progression of things we need to do. And the first thing we're going to do is add a data source. And these are all the different ones it supports, but for today we're going to use Prometheus. And you just use localhost 9090, no auth, hit save, and you get green, which is cool. Right, is everyone having luck so far or got stuck on anything? Apparently there's people here running newer than I thought.
Okay, so the best thing to do is start off with
You could also probably just edit the sources list and yeah. Yeah, there you go. Other people have done that. Yeah, because it's literally just Python, so they're all Arch any. I think there's only one thing that's compiled for C, but we won't be touching it today, so it probably, yeah, probably the same libc or close enough. Okay. So now Grafana is going to be all like, hey, you should make a dashboard. And I've made some ahead of time. So these are just linked to from the tutorial page, and you can just kind of download them, save link as, put them in downloads. And these are kind of just, these are JSON files. These aren't YAML, but that's close enough. It's a subset. Yeah. Okay. Now, adding a dashboard to Grafana is quite easy. You just hit plus, and you go import. And there's this green upload JSON. Yeah. Oh, and I put those in downloads. You can just go one by one. It's a little tedious. And then you have to make sure you click this, link it to Prometheus. Cool. And it's got data in it, which is what we want to see. So I'll just import these, and I'll tell you what they do. All right, so let's look at the instrumentation one first, because that'll actually have data in it. So in the instrumentation one, we kind of just report what Faucet and Gauge are up to. So we've got CPU usage, how many file descriptors they're using, how much memory usage they're using, and then how many times the config's been changed. So that's what we can use to track what Force is up to. Port stats is going to be interesting when we actually have some switches connected. We'll be able to go through here and see port by port what's happening. It'll also tell us our errors and discards, so we can keep an eye on those. And of course, Prometheus has a bunch of plugins and stuff you can put in for doing alerts. So alert manager is one I've used in the past, and you can just use a Prometheus expression to alert on, which is quite useful. So you could say, find any port that has a drop greater than 0, and you could page someone about that or put it into a dashboard or something. And then the last one here is inventory. So Faucet keeps a list of everything that's connected to it and some metadata about those things. So in a second, when we sped up our first switch, we're going to get some data in here. But at the moment, we can say we've got no data paths. That means no switches, and we've got no ports in our network. We have 2 controllers. So the next step is to improve that situation so that we can actually do some things. So let me just tidy my windows here. Yep.
That's all still going through that tutorial, mate?
Yep. So I'm just, the words on the page is what I'm saying. So if you get stuck or behind, everything is actually described there as well. And when I've got to the end of this, I'll pause and go around and help people and make sure everyone's good. So those were sort of like the dependencies, getting those out of the way. The next thing we've got to do is give Faucet a config. So, I should move that over. And feel free to use whatever text editor you're comfortable using, but I will use Vim. So Faucet ships with a default config. It's long and touches a lot of features we don't know about yet. So the first thing to do is just delete it. And we'll eventually work our way back to understanding what all those things do. And so we're going to start really simple today. We're going to do 1 VLAN and 2 ports. And So let me go through what this config file is. So we have top-level sections, such as VLANs and data paths, and we're going to go through a few more of those later on. But for now, we need one VLAN, and you just give it a name. That key can be anything you want. You give it an identifier, so you've got 4,095 different ones you can use. There's some reserved ones you can't use, but and then you can have a description, and that will be labeled on all the Prometheus data so that you can kind of work this out later on where your metrics line up with. And then a data path, so that has a name as well. We're going to start with a switch 1. On an OpenFlow network, every switch has an identifier, and it's just I want to say 64-bit number. I could be wrong, might be smaller than that, but we're going to start real simple here with 0x1, the first switch. Hardware, so Faucet mostly configures all devices the exact same way. There are a couple of devices where we can use some smarter things to program a TCAM layout in the switch's ASIC. But since we're just using software here, if we use vSwitch, it gives us all features in all tables, which is quite nice. And then we've got 2 ports, 1 and 2. So these port numbers map down to, so in OpenFlow, a data path has an integer for every port, which is separate to maybe the port name you might buy with the box. But today we're just going to start with 2 ports, the first one and the second one. We give them names. So we're going to be using one of my favorite things today, network namespaces, to be fake hosts on the network. They're extremely lightweight, and they're effectively kind of little container things. And we're going to spin up a bunch of these and use them to pretend to be hosts on the network. So that's what host 1 and host 2 will be, but we haven't got to set them up yet. So we're just going to save and quit that file once we've copied and pasted our initial config in. And then Faucet ships with this thing called, my mouse isn't really working, but here we go, check Faucet config. So what check Faucet config does is it parses the given config file, and it tells you what it thinks about it. So there's a bunch of implicit config in Faucet that we haven't overridden, and that's what it's printing here. So it's saying you've got 802.1x turned off. It's saying all these various options that do different features. They're all at their defaults. And then you can use this for doing error checking. So check Faucet config, if we put a mistake in here, and let's intentionally do this. Let's go yell out something for me to break in here. Shall I do a crazy VLAN number? Shall I put a hardware device that doesn't exist? Or any suggestions? Crazy VLAN. Let's also put an A in there. I think that sounds pretty cool. I actually don't know what error this is going to be, so we'll find out. OK, there we go. Vid value must be int and not string. There you go. I imagine if it was an int, it would tell us it was over.
Would it recognize if you put a tag that's misspelled?
Tag that's misspelled. So say like I have office here, but down on these ports, office A.
Well, like you got like office V. Oh, sorry, native VLAN. If it was misspelled, but native VLAN.
Oh yeah. So if I go native VLAN.
Still got your VLAN name.
What do you want me to do, sir?
Oh yeah, like that.
Yeah.
That's cool.
I might have to correct my previous mistake. I think it only tells you about one mistake at the moment. So it would go native VLAN and none. We've spent so much time making this config parser work, so it's all fuzzed. But there'll be some bugs there, but usually I'm fairly confident getting people to yell out random things and it will find it. So it knows, so we in Faucet have, in the code base, we have a list of everything that's allowed everywhere and what type it should be. And we also run PyType, which is a static type analysis for Python over all our code to make sure we're not doing weird type things. Because in Python, it's really loosely typed, and you can just randomly change stuff. And that turns out to be really bad if you expect something to be a Boolean and you get, I don't know, an object or something. So we try and be careful about all that sort of stuff. The other useful thing here is if we ran Faucet as part of a CI pipeline, so say your network is now attached to, there's a Git that has all the config files in it, you have a CI that knows how to deploy it, you can use this as a test step. So you can, you can say, hey, check the config is good before you roll it out, type of thing. So what we'll notice is So Faucet keeps a copy of this in memory. So while we've been editing this file here, Faucet's not going to touch it. But what we do here is we reload it. And so reload just sends a HUP signal. And it signals to Faucet, hey, I've changed the file. Can you go load it? So if we go look at the log file, we can see that it's done that. So varlog faucet.log. OK, so this was the config it shipped with. So we were expecting a switch 1 and switch 2, and we didn't see them. So it was just constantly logging and complaining that, hey, these important things you told me about don't actually exist. But when we did the sick HUP, so it goes reload, goes, hey, I see the config file changed. And it sees the config's bad because I didn't go and fix it. This is what happens when you ignore what your tools are telling you. OK. If it comes to a bad config, it just keeps the old config. So our network still would have been working if we had a smart config. So it keeps a copy in memory.
Okay, so what if you reboot your machine with that config?
Yeah, that would not work. Yeah, no.
It would not work, or
It would try and load that config. So yeah, so it can go from running to loading a bad config to stay running, but it can't know, a previous config. So you'd have to be.
But we'll do it atomically, I guess, is the question. We'll say if you haven't got the right config, I'm not going to start it all, or we'll start with what it can start.
Yeah, it would declare the whole thing bad, and it doesn't try and read between the lines. It doesn't try and put you into a weird state. It tries to avoid going into a state it can't ever get out of again. So I should explain some weird things in here. So yeah, this time we saw the config had changed, and we see that we need to reconfigure data path 1. So you have to do a whole bunch of annoying, painful work to make these warm reloads change. So what we do is when we see a new config file, we diff it against the old one, and we work out the minimal set of changes to get to the new config so that we can tweak all the data paths without dropping too many packets. So occasionally we give up and we do what's called a cold start. So that means you change so many things that there was no way I was going to make a useful diff. So I just turn the switch off and turn it back on again. And now luckily with OpenFlow, that's maybe a second. But if we can do a warm start, we can pretty much drop almost no packets. But this time we had to do a cold start because we changed so many things.
When you say almost, when you say almost no packets?
So it depends what feature you changed. So if you change out a VLAN number on one of your VLANs, I have to go rewrite all those rules in the switch that were to do with that VLAN, but I don't have to touch any other VLAN. So it depends as to what you change as to what impacts on the network. But because it only has to do a small number of rule changes, it is a really minimal impact. So all this weird stuff I should explain. So Faucet tries to be very kind to its hardware, and it makes really minimal OpenFlow tables. So the way OpenFlow works is you get these tables of matches and actions. And naively, you would set every table on your device to handle all matches and all actions. But it turns out when you want to compress this down to some kind of special hardware memory like a TCAM, you waste a lot of space. So we try and make our table matches really narrow. So the less you match on, the less hardware resources you have to take up. So this output here is just telling us it walked your config and it worked out the minimal set of tables that it needed on the switch. Now this doesn't matter for Open vSwitch because Open vSwitch supports everything in every table. It uses DRAM and a bunch of cool lookup structures. But on hardware, this matters. We also configure variable numbers of tables depending on what features you turned on, and that's just to keep the hardware resources down again. And we'll see here, we used to have a data path 2, but we deleted it, so it's gone away. Yeah, the next step here is going to actually be, oh, and sorry, that's probably been cutting off. Try to keep that over there. So, okay, it wants us to configure Gauge next. So Gauge comes with a very permissive config that kind of just works for everything. So Gauge knows how to walk a bunch of different stats. So we have a port stats polar, port status polar, port stats polar, and flow table polar. I'm trying to think if it has any others, but I think those are the main ones. And you can change which databases all those go to. It's far easiest just to use Prometheus for everything, but you can use like flat files or InfluxDB or something for each kind of one. And you can list which data paths it looks at, but setting all DPs just means that just blindly, whatever it talks to, it collects stats from. And then at the bottom is sort of an example of how to configure some databases. So all we're saying is Prometheus, it's on port, listen on port 000 for the fetcher to come along, the exporter, and then use port 9303 to listen on. And then, but you can use Influx and gzip, YAML and stuff. Oh, I didn't open this route, that's fine. Now, one annoying thing we do have to do each time, and I've got a bug in to fix this, but I haven't quite got around to it, is every time you change the faucet config, you've got to restart Gauge. That's because Gauge also looks at the faucet config to steal all those port labels and other nice information. So we just need to tell Gauge, hey, the faucet config changed, you should go check what the new state of the network is. Okay, so now we're going to use Open vSwitch. So I provide, at my place of work, an apt repo for the latest versions of OVS. But if you've got a version of Ubuntu newer than sort of 18.04, just using the inbuilt Open vSwitch is fine. I mean, realistically, for this tutorial, any version of OVS should work fine, but the newer ones have a lot of cool fixes and features in them. This is going to install, which version of Open vSwitch? 2.9, which is actually quite up to date. In older Ubuntus, you'll get maybe like 2.5, 2.4, which is, it'd probably still work, but it's getting a bit older there. So depending on which host operating system you've got, you can either use my Open vSwitch repo, or you can just install the ones from upstream. Okay, and then next we're going to do is I've written a bunch of bash fragments for setting up network namespaces. So all you do with these is to define them, you just copy and paste them onto your bash terminal. Sorry for anyone not using bash, I didn't bother to port these to anything else. But so the first one just creates a network namespace and gives it a name, adds some links so that we can plug it into an Open vSwitch. This next one here, as NS, it lets us run a command as a network namespace. And so once you've kind of defined these two functions, so you can just go create NS host 1 and give it an IP address. And now if we do like IP NS list, we can see we've got this faucet host 1 thing. And that's a separate network namespace. So it has all the same file system as your regular machine, but it gets entirely new network interfaces, which is perfect for what we want. So we're just going to create 2 to map back to our ports 1 and 2 on Open vSwitch. And then this horribly long command here is going to, where was it? This is going to create our Open vSwitch bridge. So in Open vSwitch, each bridge is a new switch, so you can have more than one on a machine. But today we're just going to make a BR0 and use that a bunch of times. So what we do is we set a data path ID. So in Faucet, it was 0x1. Older versions of Open vSwitch, you needed to put the entire data path ID in there. If you've got a newer one, you can just go 1, but just to be compliant with older versions, I've got the full thing specified there. We disable in-band mode, and that just cleans up a bunch of rules that it creates by default for trying to find OpenFlow controllers on your network. Because we are doing out-of-band control, we can save a few rules by turning that off. We also set fail mode to secure. What that does is if the controller goes away, Open vSwitch doesn't revert to its regular behavior of forwarding, which is a terrible idea if you're trying to build a network to have it go into some strange mode when the controller goes away. In fail mode secure, it keeps the flows that were already there in Faucet. So you can take away Faucet, and it will keep behaving as it used to. It just won't be as performant because it won't learn new hosts, but you can have a Faucet go away and the network keep working, just in a degraded state. And then what we do here is we add 2 ports. So we add host 1, host 2. We set their port numbers to 1 and 2. That's so it matches up with the faucet config. And then we do a set controller, which is what tells it to talk to faucet. So that's 6653. And then 6654 is gauge. So we'll just bang that command in. We shouldn't get any errors. Perfect. And there's this like ovs vsctl show command, which walks the database and has a look at what the current config is. So we can see we've got a bridge 0, it's got 2 controllers and is connected set to true. That means there's a TCP connection and they were able to talk OpenFlow over that. And then we've got veth host 2, veth host 1. And then I have this cool command that I sort of put together, which lets us do a bit of a fly through the network. So on my machine, we've got a loopback. Every machine sort of has that. ENS3 is how I'm getting internet to my VM. And then we have this host 1 container and host 2 container. So they're in a box because they're a separate namespace. And then we have this veth bridge. So veth is 2 ports that are connected. And so they have A side and a B side. So the B side we've got inside the container and the A side's out. And then we just plug those into Open vSwitch. And so that's how it's all kind of working. And our IP address is actually inside the containers. And so this is our switch that's under faucet control now. And if we go to Grafana and we do a little bit of a refresh of the inventory, so I didn't have to do anything there. Faucet's like, hey, there's a new switch, we should put that in Prometheus. So we can see we've got 0x1, name switch 1, it's an Open vSwitch, tells us the version and the manufacturer. So that's very useful if you've got a large network. It'll report all the firmware versions in there. And so you can write a Prometheus query to sort of build a dashboard of, hey, show me all those switches I forgot to upgrade or something like that. Or say you have a critical bug you need to fix on some of your switches, you can go see who has the out-of-date versions. So that's kind of the power of having Prometheus in there. Okay, and then I meant to show you the log files to show what Faucet is doing. Okay, so in the log file, we see that the switch 1 came up. We see port 1 has come up, port 2's come up. And then we say, okay, the VLAN office is untagged on ports 1 and 2. And then we've even got learning behavior here now. So it's seeing, that looks like v6 neighborhood discovery packets, and Faucet has now begun learning. And we can show that that's working by running this ping command. Get that off to the side. Okay. So what this command does is, as network namespace host 1, ping the address of host 2. And if we had a working switch, we'd expect some responses, which we do. So that's exciting. And then if we go check our Faucet log, so there is also an event system that Faucet has where it can like publish you these over a Unix domain socket, but we'll just use the log file because it's human readable. So actually, it had already managed to learn the MAC addresses off those v6 packets, so it didn't need to relearn. So in an OpenFlow network, you want to do as little as possible in the control plane because it's quite a constrained link. So we try and parse out every single little bit of a packet that we get over the control plane so that we don't have to keep relearning all the time. And so we managed to learn the v4 information from a v6 packet, which is handy. So the inventory one. And if we go to instrumentation, we should see that was when the switch came up. We did a spike to 0.1% CPU. Oh, and we have some more file descriptors now. We've got 11. Whew, stressful. Okay, and then the next thing we want to do is do an iPerf. So I want to show you there's no smoke and mirrors here. So I want to show that there's no software involved here. This is, well, I mean, it's all software, but I want to show that we're not switching and routing packets in Python. We're actually doing it inside the switch. So we're going to install an iPerf. And everyone here probably knows about Python, global interpreter lock. There are some limitations on how much performance we can do. But because Faucet does everything on the switch, so we'll, in host 1, pull up an iPerf server. And in host 2, we'll do a client that connects to host 1, and we'll see through our switch, we're getting 51, 53 gigabit. So I'm not doing that in Python, that all happens on the switch, because Faucet knows how to put all the right flows in there, so it doesn't need to react to every single packet. So that 50 gigabits per second, that is the Linux kernel. It's really fast. And vSwitch has to take a lot of credit for that as well. Okay, so that's, and I suppose one thing we should do is we should go look at the port stats dashboard, and we can go look at switch 1, ports 1 and 2, and it does take a couple of cycles for it to show up. So we're polling every 15 seconds, and I think it needs to see 2 of before it starts graphing. So there we go, we can start to see it appear now. Okay, so that's the sort of end of step 1. Was anyone able to follow along with that and had some success? Oh, good. Did anyone get stuck and I can answer some questions and we can try and live debug? I always like live debugging, it's good fun. No? No one with any concerns? Cool. In the later ones, we have a bit more flexibility to actually do something outside the tutorial, but for the first one, there's not much more to do than install it and see it works. In the next ones, we'll actually be writing some policy where you can think of your own things to implement rather than the things I tell you to do. So let's move on to ACLs. Okay. So since we've done the first tutorial, we can ignore this prerequisites thing. All the prerequisites are saying, please do the previous tutorial. Okay. Let me condense that down a little shorter. So we've already talked a little bit about OpenFlow as matches and actions. And so here's something interesting. Let's look at everything we can match on. Okay, so here's everything we're allowed to do a match on. And Faucet lets you do in policy a match on any one of these things as well. Because transparently, all we do is we take a Faucet policy and we make that into OpenFlow for you. So anything in here we can match on, and then we can do an action. And so an action in Faucet for a ACL is something like, I don't have them all listed here, but you can do a drop. So that's how you could do some security policy. You can do an output. That's how you could steal packets. So you used to have like span ports on switches. What we can do here is we can do TCP dump on the switch. We can push down a policy that says match on, I don't know, TCP port, I don't know, 80 or something. Maybe I want to sort of investigate a DOS or something. And I can carve that out to a specific port, or I've got a captured device, which is quite useful. We're just about to merge in a new feature where you can, I call it Faucet teleportation. You can take a packet from this switch, this port, and send it anywhere on the network, and on a different output port, and it stitches up a tunnel between the two switches and make sure it gets out there. So if you have like a real big packet broker or a packet capture device somewhere on your network, you can just tell Faucet, hey, I want to look at these packets, and it sort of works out how to get back to there, rather than having to plug in a packet broker into every single switch on your network, which is quite useful. It's also great because I might have some 100G links on my network, and I can just carve off, maybe there's a 1 megabit flow I want to look at. I can carve that off, and I can send it to a 1 gig port without having to do 100 gig capture, which is quite cool. You can also rewrite packets as they leave, so we're going to be playing a bit with that. What other things can it do? Yeah, there's a bunch of stuff. Anyway, we'll get into it. Okay, so here's the network diagram for the next network we're about to build. So we're going to keep everything in the same VLAN for this one, and we're just going to add a host 3 and a host 4 to our previous network. So this is pretty easy. So what you do is you run the create NS thing again, and I'll just pop that over to the side so you can see. So we'll make a 3 and a 4, and then this open vSwitch command is just going to plug those hosts into our bridge. So no error, which is good. And then of course we need to tell Faucet that we want to create those new ports. So we just kind of put a 3 and a 4 in here. Okay, so port 4 looks like what we had before, but port 3 does not. Port 3 has this new thing called ACLs in. And what that does is apply an access control list, multiple, to port 3. So now let's look at how you define an ACL. So I'll just copy this across. Okay, so ACLs is another top level thing. Okay. And here we've got 2 ACLs, and one of our ACLs has 2 rules in it. So you can have multiple rules in an ACL, or you can just have one. And what allow all does is basically nothing. It does the default. What you normally have in Faucet is it says every packet, all good. I'm happy with that. What block ping does is it's first matching on v4 ping and v6 ping. Unfortunately, in OpenFlow, you can't match protocol agnostic. You've got to match on the individual protocols. And what we have in here is actions allow false. That just means drop the packet. So on port 3, what we should expect is it's going to apply rules that block ICMP for v4 and v6, and then everything else will allow, because we've got an ACL composition in there. So we can go reload to apply that. Oh, I was meant to check the config, but yeah, okay, that's good, that's good. So often when I give this tutorial, I always fat finger something, and it never works until I go look at why. So now we'll find that we can't ping 3 because ping packets are dropped towards 3, but host 2 and host 4 still work. So all that's done is made a couple of OpenFlow rules, put them at high priority in an early table, and it's just dropping the traffic. So actually, we can have a look under the hood how this works. Yeah. Perspective of the port, yeah. So it's blocking, actually it's blocking the replies. So,
okay, so I was going to say, because normally when you say a switch, you block it in, and blocking from the perspective of the switch coming in.
Yep. Yep. Yeah, so I guess I lied a little bit. Yeah, it's the ICMP packets will get to host 3, but when it replies, they're blocked. We are, at the moment, working on a new feature that'll have ACLs out. It just turns out that OpenFlow makes this really, really hard to do, to have ACLs that apply at the end of a pipeline. But yeah, we've got a solution that we should be landing in Faucet soon that'll let you have ACLs out, and then we could do what you wanted. At the moment, the only way to do it is put an ACLs in on every port except port 3 and dropped it going towards port 3, which is a little bit annoying. But yeah, we'll get egress ACLs working, which will make life a bit easier. Okay, oh yeah, so I was going to show you under hood. So there's this OVS OFCUDL command for OpenFlow control, and you can go, we have to tell it we want OpenFlow version 1.3, and you can go dump flows on bearer 0. So this is what Faucet's doing. So that config that we've made is translating to 35 rules at the moment is our network. And if we grep our ICMP flows, so yeah, we'll see those ACLs have translated into these 2 rules. So in port 3, ICMP and ICMP6 drop. And that's in table 0, which is the first table where packets get processed. So that's just kind of how it's working. So the next thing we're going to do is what I was talking about at the start of this module. We're going to make a mirror ACL. So we're going to carve off some of these packets and send them to another port. So to do this, we're just going to go, oops. We're just going to add this mirror 4 to both of our actions. And so what this does is it drops the packet, but it also sends a copy to port 4. So we can prevent that traffic from actually ending up at its destination, but we can also go have a look at it in a safe place and make sure it, and yeah, see what that kind of packet's doing. So we'll reload Faucet to apply that, and then what I'm going to do is make a little new window here, which will run TCP dump as host 4. so there's no packets at the moment, but if we start our ping from before, ping host 3, so we see the packets get dropped, but they also get copied to our machine that's sitting there ready to inspect them. So you can do this with all kinds of things. So yeah. Oh yeah, so that's mirror. So mirror is the most basic one. It just blindly sort of copies things. But we can also replace this with an output, which is a bit smarter. Okay. So output will do the exact same thing. Let's just do that TCP dump. Yeah, so output, we still see the packets, they're still the same, but output has a bunch of other things we can put in here. So we can do a, we can do a set field in here. So this lets us change the packet. So we're going to output it to port 4 again, our ICMP6 and ICMP, but we're also going to rewrite the MAC address as it leaves. Okay, so if we do our TCP dump now, and we do our ping. Okay, so we see the MAC address on that packet's changed. So it used to be this BA-OB93, but now it's this. So it turns out there's a lot of useful things you can do when you can rewrite sort of parts of the packet like this. So it makes NFVing stuff really simple. So in the NFV section of the tutorial, we're going to play around with DNS. So we're gonna enforce on our network that DNS all goes to one place, and we can do this by rewriting the MAC address to point to our DNS server. And then when the DNS server gets that packet, it thinks it's for it, and you don't have to do weird things in IP tables and EB tables to rewrite the MAC address. So there's kind of some funky things you can do there if you can change the packet. Oh yeah, the other thing we can do is we can slap a VLAN on. So let's do that, because it just lets us do whatever we want to the packet. So we're going to output to, so VLAN vid, so I don't know, we'll put 300 on. Oops, that's the wrong place. Okay, so now when we reload and do our ping, so we should see in here, yeah, we've had a VLAN added. So that'll make sure that goes into the VLAN, which is useful. And there's a bunch of other stuff you can do there as well. Okay, so now I guess we should think about some other things we can do with some ACLs. You got any ideas on what packets we want to match on, or what we? Oh, what I could do is, do you want to see DHCP snooping and IPv6 router advertisements implemented here? So actually, I'll do v6 router advertisements because I don't know about you, but has anyone tried to deploy v6 and then hated when their access switches couldn't let you filter v6 router advertisements, and then your whole network just goes down one day because someone plugs in a laptop with like internet connection sharing on it or something, and it's bridging arrays everywhere? Anyone had that? Or just me? So wouldn't it be nice if we had the language where we can like write our own filtering policies? So I'm going to be, I can't remember off the top of my head, so I'm just going to copy it from one of my other repos. So if anyone was in the talk yesterday, this is the configs we ran on the conference network last year. Oh yeah, one of my other favorite ones. So usually when I build a faucet network, I always drop all spanning tree on all ports, because man, is it hard to get rid of that thing. Yeah, so here we go. So we could actually have a, v6 RA protect, and we can just copy and paste that in. Oh, and oh yeah, that looks like, oops, almost copied incorrectly. Okay, so all this does is, so we match on v6 packets, we match on ICMP6, and then we match on router advertisements, type 1, 3, 4, and we drop. And then you'd apply that to all your access ports. So let's say this was like your gateway or something. So we wouldn't protect that one, but we'd protect all these other ones. So was it v6 RA protect? And then we'll do allow all. Yeah, so just like that, you've implemented v6 router advertisement protection on a device that didn't support it. And the other cool thing here is, so Faucet works on about 6 different vendors at the moment. It's all implemented the exact same way on all of them straight away. So it's kind of the useful things we can do here. And but I've got a whole like bunch of stuff that I do with this. Oh yeah, my. Huh?
Which file in the repo?
So if you go to the. How do I make this bigger? So if you go to the sort of WAND SDN SC18 Faucet configs, so common and then ACLs. What else have I got in here? Actually, oh man, I just remembered my favorite one I do. Okay. So at work, so I have a Faucet network that drives my entire network, and I have a v6 only SSID you can join, and it uses NAT6 for translation. And I was on a call with some of my European colleagues one time, and they were talking about how much they love v6 only networks. I was like, here's the one for you. On the phone call with them, I added this policy to the network that I was making the call to them over. And so I added this to my v6 only VLAN at work. And what this does is it allows v6 and then drops every other single ether type. So no ARP, no v4. It ensures that on this VLAN, only v6 will exist. And you can do that on all the access ports of the network, so you make sure, at work I have a clean VLAN, there is no v4. It cannot be any v4. So there's literally a lot of stuff you can do with this, and it's hard to sort of scratch the surface on this, but you can sort of have your own ideas on what you want to drop, because all the matches are quite good. So, all right, did that one make sense to everyone? Should we move on, or? Anyone stuck, or everyone's good? Anyone got any ideas how they might use this? And I can tell you if it's a good idea or a bad idea. Yep.
What about private VLANs?
Yeah, a lot of people have asked me about this one, and what do you use private VLANs for? Just so that every machine is on its own L2 domain? Yeah, so
Without burning VLAN.
yeah. So we don't have a built-in primitive for that. I guess one way to do it would be to have unnumbered VLANs in Faucet, and then you could just ACL and say. So what do you have at the other end? It can talk back to a gateway or something. Yeah. You could do that with like just have a VLAN that goes nowhere, and then have an ACL that builds a path to your gateway or the set of devices you want to talk to. But there's no built-in sort of like way to do that. But it has been something that a couple of people suggested, and I've been thinking about.
It would be possible to do something like have a client-facing port that can only ever talk to the uplink port on the switch.
Yeah. Well, you could probably use the teleportation feature for that. So you could just, so if you set allow :0, so I kind of said that just drops packets, but what it actually does is it stops the packet going through the Faucet pipeline. So you can actually use an ACL to overload the Faucet behavior. So you could write an ACL that said what's allowed, and then you could say stop doing your rest of the processing, so that'll turn off Mac learning. You could do that kind of thing. But yeah, if we can sit down and have a sort of think of a good use case, I could probably build something and see. Because someone asked me one day about like how you could use PVLANs for like containerized environments, where you want a set of containers to only be able to talk to their upstream devices, but not to each other, that kind of thing. So we've also got some other funky stuff with our flooding modes. So on most devices, if you want to allow every port to talk to every other port, no matter what the settings or security policies are, you just fill the MAC table and then they flood. With Faucet, you can tell it what to do with flood packets. So on a number of networks, Faucet runs on flooding is disabled. So you can do enough broadcast to do ARP and neighborhood discovery to your gateway, and then apart from that, all broadcast addresses are dropped from the network. It turns out this can mostly work on most networks these days, which is an interesting application of SDN, I will say. All right, anyway, shall we do some VLANs after talking about PVLANs, which unfortunately isn't in this part, but we'll see how they work at least. So, okay, for this one, there's this cleanup function we're going to need to define, and that just lets us clean up after previous tutorials. So I'll just define that. And all it does is delete the bridges, delete the network namespaces, and turns off a couple of services that we'll have running in the later ones. So we'll just run cleanup, and our entire network's gone. Woohoo! Oh, we also need this ag tagged VLAN, which just lets us make a network namespace port that has a VLAN identifier on it. So we just do this IP link, add link, v0 dot the VLAN ID, type VLAN ID. Okay, so in Faucet, just like a regular switch, there's native tagged and there's mixed ports which have both. And it kind of all works how you'd expect. And for this tutorial, we're going to go a bit more ambitious with our network design. So we're going to have 3 VLANs. So host 9 is on all of them. We've got 1 to 4 is in VLAN 100. Host 5 and 6 is in VLAN 200. And 7 and 8 is in 300. And then in the box is whether it's tagged or untagged, so native or tagged. And luckily, like all the other tutorials, there is just some commands we copy and paste. So this create ns like 000, that just means create a network namespace that doesn't have an IP address assigned to it. And so, oh, I missed a bit. We also need to have host 1 and 2 in a bridge. There we go. Okay, so we made a 3 and a 4, and they are actually tagged on VLAN 100. And then we're going to make a 5 and a 6, which are untagged. And then 7 and 8 are going to be tagged on 300. And then this last one, host 9, is going to be on all VLANs, and it's got an in subnet IP on each. And then we can just plug those all into the vSwitch bridge. Okay. And now we need to do some Faucet config. So we're just going to delete everything we started with. And we're going to start with this big, horribly long thing. So the idea with it being YAML is, in reality, you'd want probably some kind of web system or configurator that automatically generates this. So YAML, luckily, is quite human readable and writable, but it's also machine readable and writable. So I usually use Ansible and Ginger 2 to generate them, but any system can kind of generate YAML these days. All right, so now we've got 3 VLANs, 100, 200, and 300. We've got the same switch, and then this is the config that maps back to that drawing we just saw. So you'll see a mixture of stuff being tagged, some on some VLANs, some on other VLANs, and that host 9's on all of them. So let's, since there's a big config change, let's do a check. We got it right, so that's good. And then we'll just do a reload into that. Okay, and then we'll do some simple inside the VLAN tests. So host 1 can ping host 2, host 3 can ping host 4, 5 can ping 6, and 7 can ping 8. Cool. But we'll note that hosts in, oh, hold on, what's that? Okay, so this is pinging between one port on native, one port on untagged. That's just regular VLAN switching, so that should be fine. But what we can do is we can add an IP address to host 5. So that's in a different VLAN. And we can add an IP on VLAN 100. And we can see that host 1, which is in VLAN 100, can't ping it. So we've got VLAN isolation. Hooray, welcome back to the 80s. I mean, that wasn't too hard. And then we'll note that they can all ping the 9th VM on all its IPs. And so, of course, if you set host 9 as a Linux device that could do forwarding, you'd be able to get through VLANs that way. But in the next section, so in the routing section, which is quite a big one, we're going to go over into VLAN routing, which Faucet can implement all your VLAN routers for you. Oh, now one thing you can do, so ACLs apply to, in Faucet, ports and VLANs, and you can apply to a whole data path, and I think that's it at the moment. So there might be some more I can miss, but generally ACLs can kind of go anywhere, which is quite nice. So the benefit of adding an ACL to a VLAN is that we do it in one rule, rather than if you do it per port, we do it for one rule per port, which isn't as efficient. So we can kind of make this block ping ACL, and we can apply this to a whole VLAN. And then now ping doesn't exist on that VLAN. And so this is how I did my V6, V4 drop rule. So yeah, so we've added that block ping to the whole VLAN. It's the same block ping from before. So notice before I reload the config, I can ping into VLAN 300. But if I reload and try again, so it doesn't work because it's now blocked for the entire VLAN. So that's a sort of optimization you can do. And it's also a good way of enforcing policy for an entire VLAN, because sometimes when you're adding stuff per port, you might miss a couple of ports. So it just lets you be a little bit more consistent. All right, anyway, this is all the real basic stuff that you've been able to do in switches forever. Let's jump ahead into, I guess, more stuff you can already do routing, but this gets a bit more interesting. So, okay, so the first thing for routing, I should just ask, VLANs made sense to everyone? Everyone can wrap their heads around virtual LANs? Yes, sir? Oh, my graph program?
Yeah.
Just have a look at what it did, or do you want to know how it works? So. No, I don't. This is just part of my random tools I use for tutorials. I could publish it. It's really simple. Here, I'll show you how embarrassingly simple it is. Okay. So there's this fantastic program called Plot Network CFG, and it knows how to talk to Open vSwitch and ask about all its interfaces. And then it creates a dot file, and there's this great Python 3 thing called xdot, which is like an interactive dot viewer. And it's absolutely fantastic. And then this pgrep just looks if it's running or not. I mean, you can take a picture of that, or I can put it up on Twitter or GitHub or something. It's like 3 lines, but surprisingly effective to explain complicated networks to people. So yeah, we can see we've got this. So this is host 9, right? So we've got 3 VLAN tags on it, and those are the interfaces with the IPs. And then we'll see it's got a line drawing all the way back to vSwitch. And so we can see all our hosts here. It's kind of cool.
So just a question about that bridge.
Yep.
Is the Linux bridge itself still doing all of the forwarding for you?
Do you mean BR0?
Yes.
BR0 is an Open vSwitch. It's not Linux bridge.
Oh, okay.
It looks like it, so it makes a network interface, but it does everything itself.
Right, so that's all happening in Open vSwitch.
In Open vSwitch, yeah. For those who haven't played with Open vSwitch, absolutely fantastic Linux tool. Drop-in replacement for Linux bridges, and does so much more. It's, yeah, really good. Can't sell enough on Open vSwitch. They're actually the reference implementation for Faucet. So before we try anything on hardware, we always try it in vSwitch first, and yeah, it usually works great there. Okay. So routing between VLANs. So yeah, let's do into VLAN routing. Okay, this is where we get to introduce virtual IPs. So Faucet, and I had this question in the talk yesterday. So Faucet's able to participate on the network. So normally a controller would be outside the network and just sort of steering things around. But you need Faucet to be on the network so that you can start talking to it. So if you want to use Faucet as a gateway, you've got to be able to do ARP for it and IPv6 neighborhood discovery to discover its MAC address, because the way layer 2 and layer 3 are separated, before we can talk it with IPs, we need to work out a MAC address first. But there are some funky hacks we were talking about at lunch where you could get rid of ARP, but anyway, for now, it makes a lot of machines work, so let's. Oh, so in Faucet, we can NFV stuff, so we can put an ACL that matches on ARP, and A, tosses it away, and B, sends it to an internal thing that learns it. Well, actually, Perry wanted to send it to a DHCP server. The DHCP server would write back to Faucet and tell it where this MAC address on the network was, and then give it its IP address, and then that would be fixed on the network forever, which turns out to be useful if you need to know where everything is and make sure you enforce policy on people. But anyway, let's. You can reuse 10.0 a lot. Or use v6. It's more of like an enforcement. So if there's not much security on a network, it's pretty easy to forge DHCP packets. It's pretty easy to set a static IP on your machine, that kind of thing. On some networks, you don't want people to be able to do that. Like if your security policy is defeated by someone changing the subnet on the machine, you probably don't really have security policy. So a lot of people kind of think the network's this magic, crazy, scary thing. But yeah, here's my tip. Turn everything off and then turn on little bits and pieces as you need it. All right, so we did a cleanup, and we're just going to create our little hosts here. So we're just going to start as normal with host 1 and host 2. And then we're going to create a bridge that has host 1 and host 2 in them. Okay, and now we're going to look at Faucet VIPs and Faucet MACs. So Faucet MAC lets Faucet have an L2 address on the network. And Faucet VIP lets Faucet have a IP address on the network. And it's a list. You can give it, well, it can only have one MAC address, but it can have as many IPs as you want. V4, V6, doesn't matter. So we're just going to do that now. So we'll just delete everything here. Create this. Okay, oh, and I'll make this a bit wider so we can actually see. So yeah, so Faucet's on the last IP address, and then a different subnet on each VLAN. And then our 2 hosts are on 2 ports. So if we relay it into that, so we don't have any kind of DHCP here, so we're going to have to manually hard code the default route to point at Faucet. So normally you'd have like a DHCP server actually assign that, rather than having to manually do it on each of your machines. And now we'll find, so we're going to use host 1 to ping host 2. And this isn't going to work because this is VLAN isolation. This is generally what you want when you have VLANs. But there's some cases where you don't want that. So we're going to create a router. So a router in Faucet has a name, like everything else, and then some config. It's called router 1, and we're just saying VLAN 100 and 200, blindly route all packets between them. We don't care. Doesn't matter. We trust them. Those guys in VLAN 200, they're good guys. Okay. So we lost the first packet there because Faucet had to do ARP resolution, so it took a little bit to respond, but there we go. Now our 2 VLANs can talk. Now, generally this is a bad idea, but what you can do here is you can actually apply policy. So on each of our VLANs, we could apply policy coming from the other VLAN and restrict what services they could talk to each other on. So we might have a server's VLAN and a client's VLAN, and maybe we just run web servers. So we could say, from the client's VLAN to the server's VLAN, port 80 TCP is OK, everything else bad. Would be one way to do it, but yeah. Okay, let's do some static routing now, because everything's going to do static routing. Sorry, all right, I kind of like static routing. It's all good. So we're just going to clean up again. And this time, so this is our network. So we've got 2 hosts in VLAN 100, and then in 200, we've got the server now. And we'll notice the server's got this 192.0.2.1 address. You'll note there I didn't use 1.1.1 because that is a real internet address you're allowed to use now, so that'd be poor. Put in documentation. Okay, so we're just going to create those namespaces. And server's going to start on this 10.0.1 address, but later we're actually going to add an IP alias for it. Okay, so now we've just set all the default routes. We need to recreate our bridge. And then we're just going to jump in. And, okay, I'll explain this. Okay, so our interface config is pretty simple. Host 1, host 2, and server. And then we got some VLANs that match. We've got our inter-VLAN router, which routes between hosts and servers. And then in our server's VLAN, we have the static route. So we say 192.0.2.0/24 can actually be found on this address. And foss is going to go, when it receives IPs with the next hop in that range, it's going to go resolve 10.0.1.1 and route all the packets there. So we'll just reload into that. Okay, and then we can test the inter-VLAN routing works. Doesn't work, so I must have messed something up. I usually do this at least once. Okay, no, that's fine. Okay, the server's there. Port 1, 2, 3. Done 10.1.1. Okay. Well, I'm still not sure what I did wrong, but this is a good way to do some faucet debugging. So if we look at the config file, so it says it wants to add, so it knows about 10.0.0.1. That's good. So, but what we see here is it tries to resolve 10.0.1.1, and it can't do that. So it's saying retry 2, 3, 4, 5. So obviously there's a problem getting to 10.0.1.1, and if we go back to our diagram, that'll be the address on here. Okay, so obviously something's wrong with our server bridge. So let's check first if it's actually plugged in. Okay, seems to be plugged in. And the other thing we can do is check it's got the right port number. Dump port disk ports. Okay, so we have port 1's host 1, port 2's host 2, port 3 is server, and they are all at 10 gig, which is good. How very odd. Okay, something weird went there wrong there. If I did a restart it, obviously a bad flow got put in there. I'll have to look into that later and see what caused that. It's not meant to happen. Okay. So, okay. So yeah, we can do that now. So we're going to add an IP alias to server.
It's definitely reproducible.
Yeah. You got it? All right.
Something happened to us.
All right. So I did all this a couple of days ago, but yeah, so one of the hardest things to get right is that warm reload. You have to account for pretty much every case. So obviously we're missing something. I will go log that as a bug. Obviously this means we don't have a test case for it, which is bad on us. We try and put tests in for everything so this doesn't happen, but I'll have to go work out what that is. So it must, yeah, I'll have a think about what that is. Okay, so now that we've added, so if we look at let's do a plot network. So if we look at our server, so we'll see it's got 10.0.1.1 and 192.0.2.1. And now if we ping that, Faucet should hopefully, okay, now it's happy. Okay, now on to BGP routing, which is a bit more interesting. So we're going to do the same. We're going to reproduce the static route, but it's going to come from a BGP controller now instead of from Faucet as a static route, which would be a more typical case. And so what we're going to add here is a BGP host namespace. And we're also going to plug in the Faucet controller into this BGP namespace. And that's just because Faucet expects to be able to actually talk BGP over an IP connection. So we're just going to plug in a cable to make that work. The first things we need to do is go delete static route. And then reload Faucet. And then we'll see that we can no longer ping that namespace address. Cool. Sorry, just the route, the static route from servers VLAN 200. So we're just going to make a BGP connection to do that. OK, so now we'll just add that namespace for BGP and plug that namespace in. And then we're going to use, OK, and then all this junk, all it does is add an extra cable that plugs between the host machine and inside to that BGP namespace, so that we can do a data plane connection to Faucet in the BGP. Okay, now we're going to use one of my favorite BGP tools, which is Bird. So we're just going to install that. It's a nice little lightweight C thing. Okay, and then by default, it's going to start on your machine. You probably don't want that, so you can go stop it. Okay, now we're just going to do, BGP in 30 seconds. It's a real easy protocol, right? Like, okay. It's only a few lines, so, okay. So protocol kernel's not too important here, but what Bird lets you do is talk to the Linux kernel over netlink, and it will like manipulate all your tables on your machine. Here we've got a scan time of 60, but we import nothing from the kernel, so that's pretty much just ignore. Protocol device lets Bird walk all its Linux network interfaces, and then we've got a protocol static. So in Bird, you get these different protocols that have names and types. So static just lets us statically route from that subnet to that IP. Now you may notice we've gone from one static to another static. Normally you would have a whole BGP infrastructure here. I just didn't want to have to set this up for each tutorial, so I'm just going to hand wave it here and say, if it can be a static route here, it can be any kind of route. It could be an OSPF route, ISIS route, whatever you wanted. The main part here is this pair with Faucet thing. So we're pairing over private ASs. So Bird's going to be on 65001. Faucet's going to be on 65000. So that means it's eBGP because they're two different AS numbers. Faucet's going to be on that 10013 address. We're going to use port 9179 instead of 179. This means that Faucet doesn't have to run as root. Because on Linux, if you want to listen on a port less than 1024, you have to be root. We think it's better to just change the port and not run as root. And then we're going to export all routes we know to Faucet, and we're going to import all routes Faucet tells us. That's all that config does. You can do a lot more, but that was the simplest I could make it. And then inside the BGP namespace, we're going to run Bird. And then we need to tell Faucet, of course, to pair with Bird. So at the moment, this isn't quite nice, but you configure BGP pairing on a VLAN, which originally kind of made sense with the way Faucet was designed, but we're going to move it out in the next version of Faucet, the next major version, which is due out next month. We're going to move this out into another router object, which makes a lot more sense. Then you don't have to tie BGP to a whole VLAN. So all we're doing here is telling Faucet, hey, listen on 9179, you're going to use 6500. Here's your router ID. Here's the address you should listen on. Here's your neighbor. And here's what AS your neighbor's using. So it's all pretty standard BGP stuff. Woo, get that moved off. Come back. And then we need to add some more IP interfaces, sorry. So we need one for Bird, and then Faucet actually lives on its own network now as a data plane. And the reason why you want that rather than just NFVing or BGP is this is a lot easier and more efficient. Before we did Faucet, we worked on a horrible tool called RouteFlow, which I hope no one here has ever heard of, but that did all BGP over the control plane, and it was not a good time. So now we can sort of tell Faucet to go try and pair with this thing. Okay, cool. So if we look at the log file, let me stop that. So BGP pairing came up straight away, and it's got the next hop and got the route already. So we can do a little bit more debugging to make sure that Bird sees the same picture. So this is the Bird command for like, hey, what do you think about Faucet? So we'll see established, we'll see it's received one route, and it's accepted one route. And so we can ask Bird, hey, what did you hear from Faucet? Sorry, what are you telling Faucet? So, hey, I'm telling Faucet 192.02 goes to blah. And then we can go ask, what do you get back from Faucet? We get back from Faucet 10.0.1.0 because that's the VLAN we configured BGP in. Okay. And now we should be back where we started. There we go. And I think I've only got like 10 minutes left, so let's quickly whip through this last example. Or otherwise it's going to be homework. I work for a university, so I assume when I come to these conferences I can still assign homework. Is that right? I'm not seeing many happy faces. Okay, so let's see what's going to be useful here. Okay, yeah, I'll do the DNS DHCP one, and then at home or in the breaks or whatever, you can have a play with doing the BGP, the DNS example, and the Zeek IDS example. They're pretty straightforward, but I think the DHCP is a good one to look at. So we're just going to do a cleanup. Okay, all right, so what are we doing here? So yeah, we'll skip Zeek, but we'll create a VLAN 200 and VLAN 300. So we'll have two hosts in each. And then we'll have a DNS mask interface that spans both VLANs. So the point of this is we want to take the DHCP protocol and we want to make sure all those packets go to our DNS server. And so Faucet's all about, if there's a good open source tool out there that does something, it can do it and Faucet will just send the packets to it. We don't want to have to write every single protocol in Faucet if we don't have to. So we created some hosts. Now we've created them all with no IP addresses because we want to see that DHCP can work. And then we've added our DNS mask server. It's tagged on all VLANs. And so we'll just create a bridge. And then DNS mask you'll have to install if you don't have it already. I don't, so we'll grab that. We can ignore that crashes on a clean install. I'm sure it's fine. We don't want their config anyway. Okay, and now we're just simply going to start DNS mask in each. We're going to start two instances in the same network namespace with different configs. So the thing that's differentiating here is, so it listens on a different interface. So one's listening on the 300 interface, one's listening on the 200 interface. And these config options just say, here's the range I want you to use. This is going to give out Faucet as the router address. So this is normally how you do it. We're also going to inject a text DNS record, which is used for the DNS part of this thing. And then we write out a lease file, and we have a log file and stuff like that. So we're just going to run those. OK, that didn't crash. So our config was better than the one that shipped, obviously. OK, and then we need to do a bit of a longer Faucet config here. Okay, so at the moment, this is just going to use normal broadcasting. So DHCP request is broadcasted to the whole VLAN, and then the DNS server, DHCP server, since it's on that same VLAN, sees the packets. We could, of course, use our knowledge from previous tutorials to assign an ACL that enforced that, but this is just using regular network semantics. And then what we'll find is if we do a reload into that new config, we should be able to run DH clients in each of these hosts, and they should now get an IP address. Cool, which they do. And I'll run a bunch of these. Cool, and they all seem to be working. And yeah, they're all getting IP addresses in the correct ranges, which is good. And then we can sort of run these commands here, which dumps all their IPs. So host 4 is on 3.11, host 3 is 3.10, host 2, 2.11, host 1, 2.10. And then we can just ping. So host 2 was 192.168.2.11. 2.11. And host 3. So this is kind of operating how we'd expect a network should work. And cool, that was quick, so we've still got some more time. So this is one of my favorite ones. So we're going to enforce where DNS goes on the network. So we're going to put a faucet policy down there that captures all port 53 traffic, UDP and TCP. It's going to rewrite the MAC address of all DNS frames and send it to a Linux box where we have DNAT, which is rewriting the IP address. Sounds crazy, but it's going to work. I believe in it. I tested this at least once. Okay, so what we can here is use the host command to look up. So 192.168.2.1 is the DNS mask server. So it's got a DNS thing working, and it's responding to this does.it.work domain that I creatively came up with. And it's going to return a text response of yes. So we can see if we directly query the servers, it works fine. If I then go and query 8.8.8, it's not going to work because there's no 8.8.8 on our network, and there's no internet here. So what we can do is we can go ask the Linux kernel, hey, what MAC address do you have for your, so this is in the DNS mask thing. So your v0, which is your default interface, what's your MAC address? So we need that for later. And then what we do is we come in here and change our config, and we're going to add an ACL. All right, so this one looks a bit scarier, but it's fine. Oh, make my window a little bit bigger. Okay. So we have this NFV DNS rule. And that's the wrong tabbing. By the way, pro tip, you're not allowed the tab character in YAML. So they got so like entrenched in their battleground over tabs and spaces that they just removed it from the language so that no one could fight over it. So the like first line of the spec is, you shall not use tabs. Oh, because you're allowed tabs. Yeah. So we actually enforce it. One of the first things we do when we check your config is check if there's the tab character. And we say, hey, you should go check that out, because everyone does that the first time. That's quite funny. Okay, so all this does is we're capturing, so it's just v4. For v6, we could make another 2 rules. We capture port 53 for TCP and UDP, and we're going to rewrite the MAC address as the packet leaves. Oops. Oops. Copy and paste. Okay, so one interesting thing I did here, I just wanted you guys to see the few different ways there are of sending packets somewhere on the network. So this is going to use faucet learning to make sure that the packets end up in the right place. Because we have that allow true there, it means when the DNS packet's gone through this ACL, it'll keep going through the regular faucet pipeline, which is MAC learning. So faucet's going to learn where that EE, E0, 0B, whatever MAC address is, and send the packets there. Now, so in Faucet, you can output packets to a port in an ACL, you can output them to a MAC address, or you can output them to another switch in another port. So I just wanted to show you that there's the different ways of doing it. So this allows our DHCP server to move around the network, as long as it's got that MAC address. And we can even add an ACL that protects that MAC address, what port it is on, or what ports it can't be on. It's always going to work, which is quite cool. So now we're just going to reload into that. Okay, and then we're going to do some magical IP table stuff. This isn't too scary, though it may look it. So we're just going to use the NAT table, which lets us rewrite IP addresses and keep state of where we're meant to send packets when we rewrite them. And all we're saying is on the 200 VLAN for UDP 53 and TCP 53, do a destination NAT, and this is the destination NAT, it's the IP address of the container. This just means that we can blindly accept any IP address that comes into our machine. And we'll keep state of where it came from and rewrite it when that packet leaves again. So we're just going to run those all in DNS mask thing. Each network namespace gets its own instance of IP tables, which is cool, so we don't pollute our regular machine. And now what we should be able to do is query 8.8.8, and it should work. And did I? This problem is reproducible too? Work for you? I'll just, okay. We'll see if it fixes everyone on the network. It does. Maybe my, did I save it? Maybe I didn't save the file. That sounds like something I would do. Oh, I'll just try to restart Faucet in case some state got stuck. Okay, so I made a mistake, obviously. Okay, let's see if our network's patched properly. So, yep, so that looks right. The only thing would be if I got the MAC address wrong. Oh, okay. I forgot to add those ACLs to anything. Forgot to apply them. Yeah. As I was. Yeah. I need to tidy this up so it just shows you the changes. Yeah, what we were meant to do is put this NFV DNS allow all. Okay. Yeah. I tried to be smart and I was once again not rewarded. Okay, so we'll just delete this and put it in. Okay, now if we run the host command, okay, now we've taken over every single DNS server on the internet. Now, this can be scary, I guess, and this is why, things like DNS over HTTP and TLS will be a good thing, but for now, that works 100% fine, and the host has no idea that we did that. So take away what you will. So I think that's probably a good place to stop. There's an IDS Zeek one you can do as well that just builds on that. But I'm happy to take any questions. Otherwise, you're free for afternoon tea, I believe. And I'll be around here to answer any questions or anything. All right, thank you, everyone.